So I want to discuss how we use our FPAA tools for the low-pass filter structure and getting experimental data with the on-chip example structure. If you're trying to look for this, what you would end up finding is you'd go under examples, look under on-chip, and you'd see the low-pass filter block. And if you did, this would be the block that would come up. And actually, you can actually go into the block and look at the resulting data that you would get out of that. Now, one of the things we did do is we already had compiled this, and you can see on the screen here we already compiled it already. So we're trying to run the taking data at this point, and you can see that we actually get experimental data. So one of the things you can of course do is get that initial plot. The plot is available, but one of the things we're going to do is just go in and zoom in and look at the data a little closer. And you can actually see now, actually what we would get is here, pretty reasonably quick step and down. Now we designed this for a corner frequency on the pretty low side. This is about 250 hertz is a rough kind of estimate that we have on this particular function. This function is a little bit forward-looking in the sense of trying to use a cutoff frequency, to try to figure out a cutoff frequency versus just simply bias currents, but that's where we begin. So this is sort of what you would imagine if you're looking at this block, and I want to come back to this block in a moment. The other thing you can also see is that the arbitrary waveform generator has its various pieces. The sample rate is again at 100 hertz, creating a step function, and we notice at this speech it's definitely going very, very rapidly without any trouble whatsoever. So we can actually go in and change some of the parameters, and one of the ones I want to show is that I want to show changing the low-pass filter parameters. Now, one of the things that we can always do is always increase our currents. So I'm actually going to increase the cutoff frequency, which is going to be the equivalent of increasing that current. I can always program things rapidly with hot electron injection. It's always when I do electron tunneling for the erase that I have to actually do sort of a global erase. So it's a block erase, but it's specific programming, very similar to what you would expect in other flash and double EEPROM type of structures. So nothing terribly surprising. But I can come in here and then I can hit this. Now you might go, well, how am I going to change it? Well, in any of these cases, typically we'll take a structure, we'll compile it up again. Now, what you do need to make sure of is that you save it before you compile it. Otherwise, it won't do anything. So that we saved it, we compiled it, and now we would normally hit program design, but since I know that I've only updated things that can either be rapidly changed, or in this case, I can actually increase the current for that, I have a different option in this case. And I would go under utilities and go to fine-tune switches. And the fine-tuning usually means increasing a current by a certain amount. Well, in this case, I'm going to be doing a fine-tuning of it, and what it allows for is a little bit faster programming and tuning, so I don't have to erase everything, and I just have to change the one or two program values that we're looking for. And then when I'm done with that, I can actually come back and do a similar measurement and see what we would get. So I'm going to clear this out. I'm going to go back and hit take data. Take data basically is, basically setting things to run mode and putting values into the register, running things and pulling out the resulting data. And what you see is actually a pretty nice result here. You actually can't even see the input in here. We'll come over here and zoom in. And you end up seeing the result fairly clearly, and actually a pretty good result as we look all the way through.